Hello, everybody. It's a great pleasure to be here and to talk to you about how to make gold. We heard gold and saw the birth of gold. At least we saw it far, far away in the distant galaxy. I want to start by explaining how this talk came about. I'm part of a project called Einstein-First, which won the Premier Science Prize in 2024. Our project is working on a modernised science curriculum because we believe every child has the right to share our best understanding of physical reality. So we teach Einstein science for children. We train teachers. We've got 55 schools currently involved and 100 teachers currently enrolled in our micro-credential courses. It's relevant and exciting science for everybody. And that gave me the opportunity to craft this talk. I just want to say one more thing about the Einstein-First project. The good news is that it changes children's attitudes to science. And particularly, what we see is a huge boost in girls' interest in science. This is teenage girls who often turn against science. We're funded by the Australian government through an ARC linkage grant with the state government as a partner and industry partners, Anglo Gold Ashanti, Goldfields, International Graphite, Excalibur, Young Engineers, and the Association of Independent Schools. So that's the context of my creation of this talk. So I want to start my talk by talking about two elements. Element 99, which is called Einsteinium. I just want to mention it for a couple of reasons. But Element 79 is really the main topic of my talk, which is aurum, shining dawn, and we like to call it Einstein's metal. This is an astonishing story of prediction and discovery. Gold was the second metal used by humans, last to be understood. Gold is gold thanks to relativity. Its colour comes about because its s orbital electron is moving at faster than 50% of light speed, and relativity tells us when things move fast, the mass increases, and also lengths shrink. And so what happens is this orbital is shrunken, and the shrinking of the orbital means that lower energy photons can be absorbed. In this case, blue is absorbed by gold, and because blue is absorbed, it's left looking gold. But there's a mystery about gold, and I want to talk about the history of the mystery. And the mystery is, where are the heavy elements made in the universe? Where is gold made? Well, the story connects to something that many of you will have seen, which is the Oppenheimer movie. We'll see how Oppenheimer comes into this, not so much because of the atom bomb, but because of something he did immediately before he joined the Manhattan Project that built the first atom bombs. So the history starts about 1932, when it was discovered that atoms have tiny balls of protons and neutrons at their core. And the particular thing was the presence of these neutrons, neutral particles. A neutron comes about if you squeeze a proton and an electron together, you make a neutron, and you measure, and also another very elusive particle called a neutrino. That was 1932. Just 2 years later, an extraordinary prediction was made by an intolerant visionary called Fritz Zwicky. He was interested in stars and exploding stars, and he got the idea that stars may explode as a result of neutron stars being formed in their cores. A neutron star would be a ball of neutrons about the size of a city. He worked all this out, but nobody took much notice because he was an intolerant visionary. And he used to say, astronomers are spherical bastards. And people would say, well, why do you call them spherical? Because they're bastards from every side you look at them, just like a sphere. But this is what he actually wrote in a scientific paper with his colleague Bader. With all reserve, we advance the view that a supernova represents the transition of an ordinary star into a neutron star, consisting mainly of neutrons. Such a star may possess a very small radius and an extremely high density. So that was their speculation. He was interested in these supernovae because they had taken place rarely over the centuries. One of the most famous ones is the supernova of the year 1054, recorded all over the world, today visible as a vast explosion in the sky. How they come about is that stars burn hydrogen and helium, turning them into heavier atoms like chlorine and iron. We're mostly made from the ashes and the unburnt hydrogen, which is all thrown out in supernova explosions. Astronomers assumed that gold, platinum, and uranium were also made. But here in the southern hemisphere, this was finally disproved. How do you tell what elements are out there? That's easy, because every atom has a light fingerprint, like these ones here, shown by these dark absorption lines. Each one represents a different element in the star, and if you can line up these lines with the light you see in it from the star, you can tell what elements are there. So my story goes on from 1934 to the next stage, which was 1939, when Einstein met Oppenheimer and academically clashed with him. They weren't enemies, but they had a major clash, as I show you here. In 1939, Einstein published a paper about Schwarzschild singularities. Schwarzschild singularities are what we call black holes today, and they were predicted immediately after Einstein's theory of gravity was published in 1915 by the German astronomer Schwarzschild. But Einstein came to dislike many of the things that had been predicted from his theories, and in this case, he wrote a paper saying Schwarzschild singularities do not exist in physical reality. He was saying that's just mathematical, it's got nothing to do with physical reality. But in exactly the same year, Oppenheimer and Volkoff, Volkoff was Oppenheimer's student, published a paper on massive neutron cores, where they did the physics of whether you could in fact have stars made of neutrons. And he showed that neutron stars were possible, but if you added more mass to them, they would get smaller, and eventually there would be a critical mass when they'd collapse. And then with another student in the same year, a student called Snyder, Oppenheimer published a paper that said, when sources of energy exhausted, a sufficiently heavy star will collapse indefinitely. This was the real prediction that black holes should exist in nature as a result of the collapse of neutron stars. So there were these two predictions, which Einstein didn't like at all. But after that, the Second World War began, and everybody forgot about these questions of astrophysics and gravity. And it wasn't until 1957 that scientists started to think about it again. And the person who made the huge contribution in that year was Richard Feynman. And many of you may have read that lovely book by Feynman called Surely You Are Joking, Mr. Feynman, which tells about his extraordinary exploits during the Manhattan Project when he played jokes on all sorts of people. But he was a great physicist who won the Nobel Prize and is celebrated in the USA on a postage stamp, as I'll show you in a moment. He asked the question, do ripples of space-time, called gravitational waves, that Einstein had predicted, really exist in nature? Einstein, who was dead by this time, had had a go at proving that they didn't exist either, even though Einstein had predicted them. Well, there's the postage stamp, and the year 1957, and the concept of gravitational waves, these waves in the shape of space, coming rolling in across the universe. What Richard Feynman did was to propose something very, very simple. He said, suppose you get a wire and you put a couple of sticky beads on that wire with some honey or something and let gravitational waves come past. Then those gravitational waves, the maths shows that they will actually make those beads move in and out. And because the beads are moving on the wire, there will be viscosity and it will get warmer, and that means that there was real energy coming in these waves. So he proved that gravitational waves carry energy, but actually he proved something else. He proved the principle of detecting gravitational waves, which was measure the distance between the beads. But of course, the way to do it wasn't with beads, but with some much, much more sophisticated technology, and that took a long, long time to come. But 6 years after all of that, after gravitational waves were proved, Freeman Dyson, who was a colleague of Einstein's, and who was also fond of pointing out that Einstein was actively hostile to black holes, he made a most extraordinary prediction. He said whether neutron stars exist is uncertain, but if two neutron stars could be put fairly close together so that they would spin around each other like this, then the consequences would be very interesting indeed. And he said, the loss of energy by gravitational radiation, by these waves of gravity, will bring the two stars closer and closer at ever-increasing speed until in the last second of their lives they'll plunge together and release a vast burst of gravitational waves at a frequency we could hear. And there would be an unimaginable intensity in these waves, which could be heard across the whole of the galaxy. He actually was suggesting that some alien civilizations might use this as a method of sending signals to each other, which sounds to me totally crazy, but the prediction, I'll show you, turned out to be exactly right. So that was 63, and then 4 years later came the big discovery of neutron stars. This was made by Jocelyn Bell, now called Jocelyn Bell Burnell, who reported unusual signals from pulsating radio sources have been recorded at Cambridge. The radiation seems to come from objects within the galaxy and may be associated with white dwarfs or neutron stars. Well, it was soon proved that these must have been neutron stars, and lots of these things, which today we call pulsars, were soon discovered. Now I'm going to jump to something that happened in the southern hemisphere easily visible from Australia in 1987. This was the first supernova since around 1600 to be visible with the naked eye. And it took place in the Large Magellanic Clouds, those big fuzzy clouds that are actually nearby galaxies in the southern sky that we can see so beautifully in Australia. There was it was really close and really bright, which meant that you could do really good fingerprinting of the light, and you can see what was present in this explosion. And there was no gold in the supernova explosions, no sign of the heavy metals that astronomers had assumed were created in events like this. This is an extraordinary object, as you can see in this close-up with these rings around it and something bright in the center. And now I'm going to just break the historical sequence for a moment, because there was a discovery made this year by the James Webb Space Telescope that sort of completes our whole story of prediction very nicely. In February this year, the James Webb Telescope proved that right in the center of that amazing object was a neutron star. And there you can see it arrowed. They could see the particular emission lines of argon, which proved that that a very strong source of high energy particles, which creates the pulses from neutron stars, from pulsars, were present in that system. So there must be a neutron star, a spinning neutron star, probably in the center of this thing. So for this particular observation, which was actually the original star, was recorded and catalogued at Perth Observatory many years before the explosion took place. And now we can see the sequence from a big star going to a supernova and finally to the neutron star. Zwicky was right. However intolerant and unpopular he was a great prophet. But still, we hadn't seen pairs of neutron stars. Actually, the first pair of neutron stars was discovered in 1976, but I'm going to jump to 2003 when Marta Burgay found what we call today the double pulsar, using Parkes radio telescope in New South Wales. The double pulsar consisted of two stars doing 10 orbits a day. So they are going very, very fast. They were very close together, and they would coalesce in an instant. At least it was what astronomers would call an instant, but to us it's 80 million years. But in 80 million years, this system would collapse in the sort of event that had been predicted in 1963. So that immediately told us that there should be bursts of gravitational waves. Probably not many from our galaxy, but if you could look at enough galaxies, they'd be happening quite often. Now let's just think about what would happen. So these neutron stars get closer and closer and closer, and eventually they get so close that they create a sort of tidal deformation on the two stars, which you can see in this computer simulation here. What's happening inside this neutron star? This neutron star is basically a huge ball of neutrons. The neutrons only exist because the stars are exerting so much pressure that the protons and electrons are held together in the form of the neutrons. Neutrons are actually unstable on their own, and they spontaneously explode. So what's happening now when these two neutron stars are getting very close? The massive gravitational pressure is being released by this tidal force. And at the point where the two stars are in contact, the gravity is zero. So suddenly, there is no longer any pressure on the neutrons. What happens to a big lump of neutrons without any pressure? Well, they start to go off like an atom bomb. And we know atom bombs are massive sources of energy. So we also know that atom bombs make heavy metals. And the metal that I introduced at the very beginning of my talk, Einsteinium, was actually discovered in the debris of an atom bomb explosion. So that seemed to set the explanation for how gold and other heavy metals might be made in the universe. When two neutron stars get together, then that could create them, as long as they could get away and not just be all sucked in to whatever the final product is. So let's just think about the energy involved in these things. Einstein taught us E equals mc squared, which basically tells us that energy has mass. And a huge atom bomb explosion, like the one where Einsteinium was discovered, releases a bit of mass, and I just want to show you how much it is. It's about 40 grams of mass, about the mass of a small Mars bar. What about when these two neutron stars come together? How much mass is released in that case? Well, the answer is So, the next part of the story is how all this got proved, because so far this is all just theory. But the theory was that gravitational waves are produced, and gravitational waves are stretching and shrinking of space that make the sticky beads move on a wire, and in these instruments, gravitational wave detectors, they make mirrors at the end of huge long vacuum pipes move closer and further apart from each other. And this is one of the instruments, which is called the Virgo detector in Italy, and there are two slightly bigger detectors in the USA. These were the detectors that finally proved the whole story. And that proof came on the 17th of August 2017. 3 gravitational wave observatories were working fine. This had taken 20 years, 30 years, 50 years before we had gone from the idea that gravitational waves existed to actual working observatories, which actually only made their first detection in 2015. So this was not the first detection of gravitational waves, but it was the detection where we discovered gold. So at the same time, the Fermi Gamma Ray Space Telescope was in orbit, working, looking at the sky in all directions in gamma rays. And it could see gamma ray photons coming from all over the universe. So we had all those instruments working at that time, and on a particular day, we heard this signal. First, we heard what we call a chirp, whoop, and finally, we heard the crash of gamma rays hitting the Earth. A vast burst of gamma rays hit the Earth 1.7 seconds after the gravitational wave signal, which was exactly the signal that we had been hoping for right from the start of the efforts to detect gravitational waves. Very quickly, this event was localized in space. Let's just first of all have a look at a little movie of what happened. There are the two neutron stars. They're getting closer and closer and closer and closer, and they're starting to get distorted by their own gravity. Eventually they get in contact, then stuff gets thrown out into space. And the most important thing is all that stuff that got thrown out into space, and some relic left behind. And in the process, a burst of gamma rays produced. So that's the gravitational wave signal, how it was created. But it's interesting to think of how fast this whole process happened. It only took 14 milliseconds to go from the top left of this slide to the bottom right. After 7 milliseconds, so first of all, they're quite well separated. 7 milliseconds later, they are overlapping like this and becoming contact. And then 7 milliseconds later, it's all finished, and it's turned into this explosion of debris being thrown out as the center object forms into something that we're not quite sure what it was, whether it was a supermassive neutron star, but we know that neutron stars have a limit to their mass, but we don't know exactly what that mass is, because we don't know exactly what the matter is like inside a neutron star. But anyway, that's the sequence, and stuff is emitted like that. That's how it might look, but this, of course, is just an artist's conception. We were too far away to see it. But they crash together, and then the next second we have a burst of gamma ray photons, just like the gamma rays that are emitted in an atomic bomb explosion. And why it was 1.7 seconds delay, we're not exactly sure, and we'll have to observe more of these to understand that. But here now is the slide of what the data really sounded like. I played you very cleaned up data, but this is the real data, and you can see that was a bit of an effort to dig the signal out of the noise, but not much, still achieved, within seconds of the signal occurring. You'll hear it in reality, how we heard it when it happened in 2017. It's just coming to the crescendo now. And so that's the signal we actually saw. And but there's more, which is the light, because these events were localized in the sky, and immediately telescopes all over the world, including a telescope called SkyMapper in New South Wales and the Zadko telescope here in Western Australia, looked at the objects that were likely to be where it came from, and they quickly found a dim little glow at the edge of a galaxy called NGC 4993, which is 130 million light years away. So we knew how far that light and the gravitational waves had traveled. And then other telescopes looked at the light in detail. And that light revealed the fingerprints of heavy metals. They were all mixed up, but they were in exactly the part of the spectrum we expect for the heavy metals. So just think about what happened now. All these things happened 130 million light years away. Gamma ray photons started their journey towards the Earth. Gravitational waves started their journey towards the Earth. They raced towards the Earth, and the gravitational waves arrived 1.7 seconds in front. Einstein had predicted that gravity travels at light speed. What we can say from this is that those speeds are the same to 1 part in 1,000 trillion. So this is extraordinarily it's extraordinary that in the very first observation of all of this, we were able to prove that Einstein was right to this extraordinary precision about his prediction for the speed of gravitational waves. This was amazing revelation. There, in this slide, you can see images taken at 3 different times of the explosion, which we call a kilonova. It's not nearly as bright as a supernova because it's not a whole star exploding, it's just a bit of stuff thrown off from the 2 neutron stars. But you can do computer simulations of what this explosion would be like, and all these atoms would have been created by this sort of massive radioactive process of the explosion, and they would be sending out dust into interstellar space. They wouldn't be sending out nice little gold nuggets like shown in that picture. All they would be sending out is dust of all these atoms. But that is the fuel, or if you like, the fertilizer for future planets. So that all this stuff mixes in with gas and other things from other supernova explosions, which finally lead to the creation of new solar systems like our own, and with it, there's the gold. So these are the gold factories for the universe. And it's nice to think what this means. If you wear a gold ring or you have a gold necklace around your neck, that was made by Binary Neutron Star Incorporated about 10 to the 10th years ago. Date of manufacture, 10 to the 10th BC. So, it's nice if you have gold, or if you mine gold, to remind people that you're finding something that was made in a most amazing process in the universe a long time ago, and it has now been able to be collected, refined, and produced in its pure form on Earth through a whole lot of processes which we're not going into today. So finally, I just want to finish with the recipe, how to make gold. The preparation time is a bit longer than making pancakes. It's about 5 billion years. The quantity you'll make will be sufficient for 1 million planetary systems. So it'll be a big, it's real bulk manufacturing. It's a real economy of scale here. So let's just go through the recipe. First, choose a pair of nice fresh stars, each about 15 suns worth of mass, and set those stars in a close orbit and allow both of them to simmer. Watch carefully as their light elements dry up. Each in turn should collapse and explode. Once the debris has cleared, confirm that you have a nice clean pair of neutron stars. Feel the gravity wave strengthening as the neutron star orbit shrinks. Now listen carefully for the chirp beginning as the stars get close. Once the two stars have reached contact, look out for exploding streams of nuclear matter. Make sure you have a fine sieve ready to collect the gold before it is spread into the galaxy. And then carefully store your gold for future planets. Thank you very much. Oh, and the last thing, no need to clean up because the hypermassive neutron star will soon collapse to a black hole. And listen carefully to this final collapse because it may contain the secrets of the Big Bang. We haven't heard that yet, and that's the next challenge in gravitational wave astronomy. Thank you. That's the end of my talk. A great pleasure to have been able to talk to you about where gold comes from.